this video, I'm going to go over how to solve systems of ordinary differential equations using the forward Euler method. So we have this iterative formula here with the identity matrix, step size of 0.1, and another matrix A, which we're going to calculate, and that uses the initial conditions as well. So with this one, we have the second derivative plus 2 multiplied by the first derivative plus 3y equals 0. So if you write it out, we have y1, y2, and y3, which is equal to the derivative of y2. So in matrix 1, we have y1 and y2. So the derivative of y1 is y2, and the derivative of y2 is y3. But we also have the derivative of y2, which is equivalent to the second derivative in the equation given. So if we move this portion to the right hand side of the equation and add it in here, we would have minus 2y2, because the first derivative is equivalent to y2, minus 3y1. I have another video explaining how to reduce a higher order ODE into a system of first order ODEs, as I've done here, and that video explains how to do everything. We also need the associated initial conditions, so we have y1 and y2 at 1, and they are 1 and 0. So we now need to convert this into a matrix. So the matrix would look like this, y1 and y2. So I also have another video on multiplying matrices, which is what you need to do for this. So it'd be 0, 1, minus 3, minus 2. So we have 0, y1, y2, minus 3y1, minus 2y2. And this is the matrix of A, which is what was in the equation up here. So now we're going to use the equation and determine y of 1.2. So we would have y1 0.1, because we're only having h equals 0.1 as a step size, so we have to do this twice. That equals, so we have the identity matrix. So the identity matrix is 1, 0, 0, 1, and then that is plus the step size, so 0.1, multiplied by A, so it's 0, 1, minus 3, minus 2, and then we'll close that bracket, and that's multiplied by the initial conditions. So the initial conditions are 1 and 0. We identified that here and they were given in the equation. So 1 and 0. So now that we've done that, we're going to multiply everything in here. So y1 plus 1. Still have the identity, plus another matrix, so 0, 0.1, negative 0.3, and negative 0.2. And that would all be multiplied by 1, 0. Then we add these two matrices together, so we have 1, 0.1, negative 0.3, and 0.8. That's multiplied by 1, 0. So now that we've done that, if we calculate that, so we have 1 plus 0 and negative 0.3 plus 0. So that's what we're going to use to find 1.2, because this is y 1.1, so we have to do it again. hence the iterative forward Euler method. So we do the exact same method again. y1.2 is equal to the identity matrix plus 0.1 plus a, which is 0, 1, minus 3, minus 2. And that's times by the previous answer, so the one we've just calculated, 1, negative 0.3. If we work everything out, we have 1001 plus 0, 0.1, negative 0.3, and negative 0.2. And if we work across, we add the matrices together. We have 0, oh sorry, that should be 1. We have 1, 0.1, negative 0.3, and 0.8. Then we multiply that by 1 and negative 0.3. So, using matrix multiplication, we have 1 minus 0.03, and then we have negative 0.3 minus 0.024. Oh, sorry, that should be minus 0.24. Extra 0 for some reason. So then we're going to add or multiply, add and minus. So we are left with 0.97 and negative 0.54. So the answer we want, because remember here we had the answer for y1 and for y2. Remember y2 was the derivative of the first one, so we want y1, which is the top. So our answer is 0.97. And that's it. That's how you use the forward Euler to solve a system of ODEs.